Today we're going to be looking at a linear regression t-test, and to make this easier on myself and you, I've typed up pretty much the entire test for you so we can just kind of fill in the blanks. This is a weird one because I've actually never seen them on an AP exam have you do a full linear regression t-test. I think there's maybe one or two homework problems that's going to ask you to go through this, but usually what they'll do is they'll give you a computer printout. But there's a couple weird things that show up, and so let me show you how we work around those, and then we'll do a computer printout example. So what we're going to be looking at, so if you would enter waist in L1 and body fat in L2, like I have done, so if you want to pause it and get that going, we go through, and the question that we're seeking out when you're doing a linear regression t-test is there a linear relationship between these two things? And and we've got plenty of other options. We can take a look at a scatter plot, and of L1 versus L2, see how strong of a linear relationship it looks like. And it does look like there is a linear relationship, but it turns out there's actually a test that will let you know if there is. So, when you're doing linear regression, it's always the stat calc 8. Everyone always wants to go to stat calc 8. L1, L2, press enter. And what you're going to notice is you just took one sample of 20 people, and of those 20 people, you guys computed a least squares regression line. Now, what we're wondering is if we go to another 20 people and another 20 people and another 20 people, and we calculate, we're going to come up with different least squares regression lines, will there still be a linear relationship, if we look at another 20 people? So this is just our one sample. So what it's all about, everything you do is about the slopes, B. Right now you have a sample slope, okay, and your equation is predicted body fat percentage is equal to negative 62.56 plus 2.22 times the waist size, WS, waist size. And if there was no linear relationship between these two variables, you would find that the slope would equal 0, and you would just have, the y valuing equaling one number, and when that happens, that would be the line would just look like a horizontal line. So no relationship would have a slope of 0. So what we're going to do is, when you start this test up, is, your HO and HA are slightly different. We are going to assume that there's no linear relationship. So we're going to assume that the population slope is 0. That's what beta. Beta is notice I define it down here, the population slope of the least squares regression line of breastfeeding percent on waist size. Okay, the sample slopes, these are slightly different variables. Sample slope is 2.22 and n is equal to 20. There's this other variable we're going to need, hold off because we don't have a way of getting it just now. We have to actually use our calculator to help us with that. So HO, you're going to have to study this. There's no linear relationship. B is equal to 0. B is not equal to 0. There is a linear relationship. So conditions for a linear regression, it's actually a t-test, and when you're doing a t-test, you have to worry about degrees of freedom. In this situation, it's actually n minus 2 degrees of freedom. Think of it as two variables, waist, body fat percentage, so that's why you actually take n minus 2. Number 1, simple random sample. Number 2, population of adults greater than 10 times n. Okay, we're good to go. Then we get to number 3, 4, and 5. Okay, so here's what we got to do. We're going to look at a couple things, and we're going to state, residual plot shows no scatter, no pattern. Residual plot shows little to no skewness or extreme outliers. So let's take a look at a residual plot. Residuals get calculated every time you do stat calc 8. So I'm good to go. Residual plot, go to right here. You're going to do L1 versus residuals. go to the list menu to grab the residual list and do zoom 9. Okay, scatter, no pattern, give me a quick little sketch of that. So let me put this down over here. So look at a residual plot. And we are doing waist size against residuals. Okay, so I'm going to draw a residual plot, and we're going to comment, it shows scatter and no pattern. That's good. A linear model is good. We also want it to show little or no skewness or extreme outliers. So, like, skewness on a residual plot would look something like where it fans out. This would have skewness, if that makes sense. So it's kind of like fanning out. That would be skewness. And then like an outlier would be something that's like way out there, okay, outside of the pattern. So our residual plot looks good. Okay, and then the last one we got to look at is we need our residuals to be approximately normally distributed. So we are going to look at this thing called a normal probability plot. We've looked at it once probably in your life. You probably don't remember. Go to your plots. And it's the very last one. Actually, this was a test question on it where that's a normal probability plot right there. We want L1 versus L2. Okay, do zoom 9. Oh wait, whoa, I have to highlight it. Press enter on the last one. Press enter. Make sure it's highlighted. Data list is L1. Data access looks good, X. Okay, just leave it like that. Zoom 9. And here's what you need on a normal probability plot. If it is a straight line, that means that your data is approximately normally distributed. If it is, it's like kind of tilts like that or something like that, that would be, I think, skewed to the left and then skewed to the right. There's a handout I gave a long time ago. What we need is a straight line. So let's sketch this picture. Look at a normal probability plot. Where can we put that? Right here. And do a quick little sketch of that. It's not going to be perfect because I think there's like 2 here. But do a better sketch than I'm doing, please. Just sketch that data right there. And what we need, so make a little note to yourself, is we need a straight line. In a normal probability plot for it to be normally distributed. Okay, so there actually is no 3 dots or anything to worry about after these. Just proceed after you show residual plot and the normal probability plot. So we're doing a significance test in the same way that we would use in the past. The Greek letter goes in the middle. The Greek letter, the null hypothesis, is 0. Now, you're very generic. If I look at my Lime sheet, it says to find the test statistic, you would take the statistic minus the parameter divided by the standard deviation of the statistic. Okay? So that's page 5. It hasn't changed. Now we're dealing with slopes. Everything you do is about slopes, slopes, slopes. So we're taking the English slope, B, minus the Greek letter, beta, over the standard error, because we don't know population standard deviation of the slopes. Kind of how it was like the standard error of the mean or the standard error of the proportions. So here's where the test gets tricky, and I really think this is why they don't make you go through a whole entire significance test. The problem is that to calculate your t-value, you need the standard error of the slopes, which I wrote up here with a blank. You don't know the standard error of the slopes. So we have to kind of go backwards. I'm going to go do the significance test. Stat test. And it's actually letter F, linear regression t-test. And make sure you're doing L1, L2, you're doing a not equal to, hit calculate. And you're going to copy down your t-value, copy down your p-value, right there. Notice our degrees of freedom are 18, n minus 2, so it actually gives it 2, so you don't have to guess. Now there's something else that shows up here. That S, see that 4.5396? This is not the standard error of the slopes. It is the standard deviation of the residuals. That actually is given in the computer printout. So do not use that S. So just copy down your t-value, p-value. And so here's what's going to happen. And this is kind of what I need you to take from this so that you can do the problems that are not full significance test, is the relationship T, let me write this over here. T is equal to B minus beta over the standard error of the slopes. Well, B is usually going to be 0. In fact, it is 0. So just, we're assuming there's no linear relationship, so B is equal to 0. So essentially, this is what you guys need to remember, is that T is equal to B over the standard error of the slopes. Okay? So if I give you the t value, 8.1437, and I know what b is, then what I can do is I can solve and say that the standard error of the slope is equal to, these just switch places, 2.22 divided by 8.1437. So t is equal to b over standard error, or you can say standard error is equal to b over t. Okay, you need to know this. Okay, standard error b over t. T is b over, these essentially just switch places. So what we're going to do is we're going to take 2.22 divided by 8.1437. That's going to give us the standard error, which is 0.272. And put that up here. Okay, so it's so backwards. And then we can make our conclusion. So since the p-value equals 1.89 times 10 to the negative 7 is less than alpha, we reject HO. There is sufficient evidence to conclude there is a linear relationship between waist size and body fat percentage. Okay, so it's a little weird, and I think it's because of this that they don't make you do a full test. Maybe they will this year. I haven't seen it yet. So usually it's a computer printout. So please, whatever you do, I need you to, you can use this to do your homework when they ask for a full problem, but this is really what I need you to see, is the relationship between T and the standard error. So, and it just comes from B minus beta, but beta is equal to 0 divided by the standard error. So if I give you T, you can find the standard error. If I give you the standard error, you can find T, and likewise, you can find B from those as well. Now, a confidence interval, this should be a multiplication sign. You start in the middle with B. So in a confidence interval, you would be putting 2.22 in the middle. Okay, so B plus or minus T star times the standard error of the slope. So it's kind of backwards, is you would actually have to go do a significance test first to figure out what the T value was, to then go back and get the standard error that you would need in your formula for confidence intervals. So statistic plus or minus the critical value t star times the standard error of the slope. That's from the Lime sheet, page 5. And then I can just go to the calculator and do stat test, linear regression t interval, and L1, L2, 95, hit calculate, and there's your confidence interval. Okay? So that's how you would turn your significance test into a confidence interval. So I'm going to stop there, and then I'll show you really how we're going to handle this using a computer printout, which is most likely what's going to happen to you if they ask you to do any linear regression. So there are a couple of things that you really do need to take away from this, though. So I will catch you in the next video.